Okay, so first up we have Jack Neubecker from the University of Queensland, and he'll be talking to us today about Hamilton decompositions of infinite graphs. If you have any questions in the chat, pass them to me or enter them in the chat and I'll bring them up with Jack. Thank you.
Okay, thanks for the introduction, Jeremy. I will be talking to you today about Hamilton decompositions of infinite graphs. This was work done during my honours thesis under the supervision of Barbara Manham. The aims for today, at the very least, what I'd like to do is introduce an intuition for Hamilton decompositions of infinite graphs. If you can understand why I think the picture that I've got on the right is so beautiful, then I'll consider that a win. Beyond that, it would be nice if we could notice some similarities between graphs we do know how to Hamilton decompose and graphs which, as of right now, we don't know whether we can or not. And in a perfect world, someone somewhere in the talk notices a beautiful and unique pattern, and we can use that to build some beautiful mathematics. But I'll probably just settle for the first two if we can get that done. Brief disclaimer, a lot of the pictures in here look really nice like this. I spent a lot of time on them, putting them into my honours thesis. And some of the pictures I've had to make under a bit of time pressure, so they look like that. But hopefully it doesn't detract from the story that I'm trying to tell, and you can tell what the picture's meant to be doing. So what do we all need to agree on before we get started? For those who aren't familiar, Hamilton's cycle in a finite graph is a path which starts at a vertex, visits every other vertex exactly once, and returns to where it started. So for example, the blue edges in this graph are an example of a Hamilton cycle. Beyond that, if I can color all of the edges of my graph so that each color is a Hamilton cycle, then I will call that graph Hamilton decomposable. So we can see that not only do the blue edges form a cycle, but the orange edges do too. So we can say that this graph formed by their union is a Hamilton decomposition into cycles. So some obvious necessary conditions that it's good to wrap your head around. The graph has to be even regular, as every Hamilton cycle is too regular. It goes in and it goes out. And so overall, we have to have an even number of edges coming out of each vertex. And as I pull these Hamilton cycles out of my graph, I need to make sure that I don't accidentally disconnect the graph before I pulled out all of the edges. So we're also going to say that the graph is 2K edge connected. And you can just think of this as a well enough connected condition. And other than that, we don't really have a lot of great tools for telling when a graph is Hamilton decomposable in general. So, but I'm here to talk about infinite graphs. What do we mean by an infinite graph? Well, formally, a graph is just a pair VE, where V is a vertex set and E, the edge set, is a set of two subsets of V. If I only make E infinite, then we don't get a very interesting graph from a Hamiltonian perspective. So let's at least make V infinite as well. But I'm also going to make sure that V isn't too infinite. If it's uncountably infinite, then anything like a Hamilton path where I visit all of the vertices isn't going to be possible because we can't count all of the vertices. So we're going to say that our vertex set is countably infinite today as well. And just because the maths is a little bit easier, we're also going to say that our graph is locally finite. So basically every vertex only has a finite number of edges coming out of it. There are some interesting non-locally finite graphs, but they're a completely different animal. So how can we have a Hamilton cycle in an infinite graph when we have to visit an infinite number of vertices before we return? Well, we can't. So what we do instead is we define what's called a Hamilton double ray, which does the same job. So to start with, we should talk about a one-way infinite path, also known as a ray. It starts at a vertex V0 and extends off in one direction off to infinity, and each vertex is unique. Now, if I can find another ray that also starts at V0, but heads off to the left instead, again, unique vertices except for the root vertex, then I can glue them together to create what we call a double ray, because it extends off infinitely in two directions. And you'll note then that this is too regular, just like a Hamilton cycle is. So if this happens to visit every vertex, then we'll call it a Hamilton double ray. And the goal of a Hamilton decomposition is that we want to color all of the edges in our graph so that each one of those colors forms such a Hamilton double ray. So what does that look like in practice? Well, a classic example of an infinite graph is the two-dimensional grid. You can see here that I've drawn in a spiral in orange. We can think of it as starting at the origin here. One arm goes this way, the other arm goes this way, and they kind of spiral around and join up with each other and then start spiraling out like this. And you should be able to see that eventually I'll hit every vertex in the graph. And there's lots of ways of doing this. That's not particularly impressive, but if you do that without too much thought, then the edges you get left behind with probably won't also form a Hamilton double ray, which is what we want. But this one does. If you color in the remaining edges blue, then what we see is another blue spiral, which is an exact copy of the orange graph, just rotated by 90 degrees, which I think is a very beautiful construction. I haven't seen it anywhere else, but I'm convinced that it must exist out there somewhere on some sort of ancient pot or something. But I haven't seen it yet. If you do see it someday, please let me know, because I really want to know that I'm not the first person to discover this nice pattern. Anyway, let's understand a little bit more about the structure of an infinite graph. So an important topic that we need to get into our brains is the notion of the ends of a graph. So intuitively, an end of a graph is a direction in which the graph extends to infinity. Finite graphs don't have ends. That's an easy one. The ray that we saw earlier has one end. It only goes in one direction. The double ray has two ends, and I can glue as many rays as I like together to form a tree with as many rays as I feel like. Oh, sorry, I should say as many ends as I feel like. Up to and including uncountably infinite ends, as we can see in this complete infinite binary tree, which is a rather stunning result when there's only a countably finite number of vertices in that graph. But that's a topic for another time. We can formalize the notion of ends a little bit more concretely by distinguishing them based on the rays that are or aren't in them. So we can define two rays as belonging to different ends in two equivalent ways. Either we can say that they're different if there is no ray R, which contains infinitely many vertices of both of the rays that we're comparing, or if there is a finite vertex cut, which leaves only finitely many vertices from our two rays in the same connected component. So I've drawn down here a ladder graph, and let's start by comparing R1 and R2. It seems like they're both going off to the left. And so we can prove that by showing that there's this purple ray R, which snakes up and down between the two rays, hits infinitely many of the vertices from both. And so that's a way we can convince ourselves that R1 and R2 belong to the same end. By comparison, R1 and R3 seem to be going in different directions. And we can show that by providing this vertex cut C, wherein the vertices of R1 are all on one connected component, and the vertices of R3, except for the root, are all in another infinite component. And so we can say that R1 and R3 are separate because there's no purple ray that we could draw that connects these two, because we can only go through this vertex cut twice. Okay, so just to make sure that we really understand what ends are, let's talk about why the grid graph only has one end. Intuitively, you might think that it's got an infinite number of different directions we can go, but so let's pick a pair of rays that seem to be going in very different directions. Say the x-axis negative and then x-axis positive. Well, you can see that the spiral that I've drawn here is going to circle around and eventually hit as many vertices of my two rays as I would like. Similarly, if I wanted to find a vertex cut that separated these two into different infinite components, it would have to cut out an infinite number of vertices. Say if I took out the y-axis, that's an infinite number of vertices, which we don't allow. Okay, and so if you're familiar with projective geometry, you might want to call that just the out direction that we might just label with the one infinity if we needed to. But we're not going to actually label any infinity points in what we're doing today. So why do we care about ends so much? Well, at a very obvious level, I can't have a Hamilton double ray in a graph that has more than two ends, because a double ray only has two ends. There's no way I can visit three different ends with a two-ended graph. So let's say from now on that our graph has to have one or two ends. Otherwise, it's just not possible. Well, even once we've constrained ourselves to that, in the two-ended case, there's a very particular thing that we have to be careful about called finite edge cuts. There should be an edge there, but I only just noticed that. So let's consider this triangular infinite prism. In particular, let's look at this edge cut that I've highlighted in dotted blue edges. Clearly, if I remove these, then the graph has two separate infinite components, one on the left, one on the right. Well, you'll also notice that this graph is four regular, which means if I color the edges into Hamilton double rays, I would need to use two colors. Well, each Hamilton double ray needs to use an odd number of dotted edges because it needs to have one end on one side and one end on the other side. How many times does it cross over? It has to be an odd number of times. Well, it's not hard to convince yourself that you can't add up two odd numbers and cover these three edges. So we can comfortably say that it's just not possible to Hamilton decompose this graph, which is a shame, but it's a fact. So in general, when we see a finite edge cut like this that proves that we can't decompose the graph, then we will say that it is inadmissible. Whereas if we can't find such an edge cut, then we call it admissible. And it's not hard to convince yourself that if this was, for example, the pentagonal-based infinite prism instead, then we would run into the same problem. Two odds can't make five. So in general, all odd-based infinite prisms are inadmissible. Well, what about even-based prisms? Well, there's a rather simple pattern that we can exploit to decompose any even-based infinite prism. So if you imagine taking the prism that I drew before and kind of looking down it from the inside, you would see one end extending into the page, one end extending out. And that's, in a lot of ways, a much easier way to actually draw these graphs. So you can see the decomposition by starting at this vertex 0. If we follow the blue edges, we see that we jump up and down, following the cycle in one of the bases, well, in two of the bases really, but it's the same cycle, jumping up and down until we get back to where we started, in which case, instead of jumping back up and forming a closed cycle, we jump down, and then we repeat the same pattern over again. So we get this rather nice property that our double ray has this kind of translation symmetry. And not only does that double ray have this translation symmetry, the edges left behind in orange have exactly the same symmetry. You can see that the blue edge, if I just moved every edge into the page a little bit more, that we would line up exactly with the orange edges, which is rather nice. So we get this decomposition that has a nice translation symmetry that lines up perfectly with the symmetry of the prism. So let me formalize a little bit more what I mean by these infinite prisms. If you're familiar with the Cartesian product of graphs, then it's the standard definition. If you're not, don't worry too much about the notation. Let's just talk about the intuition. Basically, we can take a pair of graphs, say in this example, K2 and K4. And if I blow up each vertex of my first graph with a copy of my second graph, then connect all of the equivalent vertices in adjacent copies, then I end up with this prism like this, which is rather nice. And you can imagine instead of K2, if I had a longer path or even an infinite path, I would just get a longer prism or the infinite prism that we saw earlier. So there are a lot of conjectures and results for Cartesian products of finite graphs. So it's kind of nice that we can notice this similarity. And in general, we'd like to kind of extend as many of those results as we can to infinite graphs. But because of the different ends that we can get, it's not always that easy to just extend them the way you might think. So this basic theorem that based on this obvious pattern between stepping up and down like this, we can eventually prove that for any even cycle Cn cross P infinity, the infinite prism with base Cn has a Hamilton decomposition. And of course, we've seen that if n is odd, it's just not possible. Well, one of the main results that we were able to prove is that this is also true for higher degree base graphs. So notice that Cn is the only Hamilton decomposable two regular graph in general, there's a lot more for regular Hamilton decomposable graphs. And we were able to prove that as long as G is Hamilton decomposable, then its infinite prism is as well. Again, under this edge cut condition that we wanted to make sure of. And we were able to show the same for 6 regular graphs as well. So we can see here K5 cross P infinity. If you look at the outermost set of vertices, you can see K5 kind of floating around the outside. It's Hamilton decomposable, and we can show that its infinite prism is decomposable as well. When you've got a 6 regular graph, it becomes a bit difficult to draw all of the decompositions at once. It just becomes too messy. So I've just drawn one path here. And the idea is we can slide this up and down as much as we like to get the rest of our decompositions, our double rays in the decomposition. Okay, so what about the one-ended infinite graph? So far, we've just talked about two-ended infinite graphs. Well, another set of authors, Erdelehner and Pitts, focused on that case. We've already seen the 2-dimensional grid. You can convince yourself that that's the Cartesian product of 2 double rays. You've got ray, 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 and you connect them all up like that. Well, what they were able to show is that any n-dimensional grid also has a Hamilton decomposition, which is rather lovely. So we've already seen this nice construction for the 2-dimensional grid. And so what I wanted to do is try and visualize what the 3-dimensional construction looks like. And that's the best attempt that I could get. It gets very hard to keep track of so many copies of the 2-dimensional grid all on the same page without the edges just like running over each other like too much. So I just thought I have to actually put this in 3 space. And this is the best that I could get. And okay, I know what you're thinking. At some point in my thesis, I just lost the plot. Fern, that is an excellent suggestion. Thank you for that. I will definitely follow up on that idea. Yeah, in the meantime, yeah, like this is just a problem with trying to extend to higher dimensions. I would like to visualize this better. Minecraft is an excellent idea, but I'm also keen to hear any nice computer visualization software for rotating things around that people might have. Anyway, so Erdelehner and Pitts were actually able to prove a much stronger result than the one that I just stated. In particular, they proved that if G and H are both infinite and Hamilton decomposable, then G cross H is also Hamilton decomposable. And to see that this is a truly stronger result, note that each of our component graphs in our grid graphs are like trivially Hamilton decomposable because they're just double rays. So let's examine some examples. Well, we already know that C4 cross P infinity is Hamilton decomposable. So let's product it with the Hamilton double ray like this, and we get this 4-cycle cross with the grid. You can think of it as 4 grids laid together and connecting their equivalent vertices in a cycle. Or you can think of it this way, as a bunch of prisms all connected to each other. Well, thanks to Erdelehner and Pitts, we might not exactly know what it looks like, but we know that it has a Hamilton decomposition. And the same goes for any even order cycle that we product with, like so. Well, why can't we do the same for C3 cross P infinity squared? We get a graph like this. Why can't we decompose it the same way? Well, recall that we actually couldn't decompose C3 cross P infinity because of that edge cut condition. So we can't use the result of Erdelehner and Pitts to prove that the graph on the right has a Hamilton decomposition. But it really feels like it should. It seems like there's a very similar structure between these odd order graphs and the even order graphs. But it just seems that we need a better understanding of exactly how those decompositions actually look to kind of fill in all of those odd cases. So at the moment, we don't have a result here. You can start playing around with it and you might see, you might be able to get so far, but exactly how you would continue this off to infinity is not particularly clear. It seems that these little cycles all the way just kind of get in the way a lot more than you would expect. Okay, so I'm pretty much out of time, so I won't have time to talk too much about these interesting questions. Maybe people can just ask them if they're interested. Otherwise, thank you for listening.
Okay, so thanks, Jack. Everyone give him a round of applause through your reactions or through the microphone.
Thank you.
Do we have any questions? We have one question that was already given during the talk.
Okay.
Someone wanted to know if we can cover, I think it was the grid, like the two-dimensional grid. Sorry, I can't think of the word right now. Yes, that one. Is it possible to cover that in more than 2 rays?
What do you mean by cover it? As in like?
I think decompose it into more than 2 rays.
Yeah, so because the graph is 4 regular, each ray has to be 2 regular on each vertex. So you can't, so yeah, there's exactly 2 double rays in any decomposition of this graph. Of note, I think, is that, you know, this one's a rather nice example, but you could imagine deleting any kind of finite chunk of this graph. And there's a bunch of ways that you could fill in that chunk in a much less beautiful and symmetric way and still get a decomposition. So there might not be, there in a sense, there is a lot of different ways to decompose the graph, but I think here is the nicest one. Though there's it's a hard way to quantify exactly what it means by nice.
I had a question as well about that proof. I can't remember the authors that did it, but the Cartesian product between 2 ones that are Hamilton decomposable are Hamilton decomposable.
Yes, so this one.
Is that a non-constructive proof?
It's constructive in a sense.
Yeah. Okay.
I'll illustrate what I mean with a few more pictures of those clay stick and ball diagrams. So basically their proof involved extending out the paths, like finite paths, by a little bit each time and continuing to repeat that process and showing that you could always extend it out by more. So you could imagine starting at the origin and just adding the one green edge here. Okay, well then now we have to cover that, all of the vertices that the green path covers with our orange edges. So we kind of add that little half square like that.
Right.
Well, then what comes next? Well, now we have to add the purple path. And so the purple path kind of squiggles around and makes sure to touch all of those vertices. And each time we kind of grow the graph a little bit more. And basically you just have to argue why you can always add a little bit more, which works. But like the way that they proved you can always do it, it feels very unconstructive. I haven't like formalized whether it's purely constructive or not, but as you read it, it feels like there's a lot of different ways you could actually do each step, and most of them aren't elegant, if that makes sense.
Yep. Someone in the chat gave a link to another graphics thing that you might want to look into.
Okay, cool. If it gets a better result than scribbling it down on the notes app on my phone, and then it sounds like something worth trying out, but thank you.
Jody wanted you to go back to a certain slide. I'm not sure which one she was referring to.
Was it this one, Jody, or?
Yeah, it was this one.
Okay. Yeah, we didn't really have time to, I planted these questions just in case I had plenty of time at the end of my talk, and there were plenty of talks from the audience. So if you're still interested in any of these, maybe it's a talk for GatherTown later. How are we doing for time?
We've got 5 minutes until the next talk.
Okay. So. Is there anyone in particular, Jody, or?
No, sorry, I'm just thinking about them.
Okay.
They do seem quite interesting.
Cool. Well, some of them, my only answer is I don't think so, but you can't rule it out. But yeah, Jeremy's question was basically asking question 4, and yeah, we briefly kind of touched on the third one. So yeah.
Can you talk a bit more about asymmetric constructions? Because all the pictures you showed us are just really nice.
So the grid that we've been referring to a lot, I mentioned, I'll just use this one because it's here. Like I mentioned that you could kind of take out a chunk of the graph, and inside that chunk you could recolor in the edges in a different way, just playing the same kind of finite maze game that you normally play with Hamilton graphs. and come up with a different construction that's, you know, still a decomposition, but now no longer has this nice rotational symmetry. And in one-ended graphs in particular, it seems that because there's just so much space outside of what the finite chunk that you're looking at, it seems that there's always a heap of space for you to do these kind of lazy is the wrong word. The easy thing, which is just do it in the most inelegant way possible, just to get the result. But I don't know, the fact that the two-dimensional grid has such a nice construction, if you find it, it feels like there should be similarly nice constructions for the other ones as well. Like, especially with the grids, like the grid has this nice order 4 automorphism, right, where you rotate by 4. And this deconstruction has very particularly exploited that. Well, the Z3 graph has a very similar kind of order 3 automorphism by permuting all of the basis vectors, I guess. So it feels like there should be some nice rotation between the 3 Hamilton double rays in that decomposition as well. But yeah, it just gets very hard to actually kind of keep track of that as you go.
Yeah, that makes sense. Does any of the proofs actually require it to have that nice rotational symmetry, or
No.
is it really non-constructive proofs?
Yeah, it makes the proof really easy if you have a nice symmetry, because you can just tell us what the symmetry is. Yeah, for Erdelehner and Pitz's construction, they were kind of using the symmetry in a sense to show that you can always do the like zigzaggy thing you need to, but the end result never ended up with any symmetry, or at least doesn't necessarily end up with any symmetry.
Cool.
So yeah,
Thanks
we
for
haven't even
answering the
touched on,
question.
no worries. Like you can also call these Cayley graphs, which, you know, if you're a group theorist might sound exciting. Didn't really touch on that, but that's another way that you can view all of this. Okay.